you can engineer against an earthquake like this. So this was largely a preventable disaster.
Welcome to Geology Talk, our monthly gathering of geology enthusiasts. My name is Paul Edison Lam. I'm a communications director of the Geological Society of the Oregon Country. We're going to be talking about Turkey and Anatolia today. And one of GSOC's commitments is to earthquake awareness. That's certainly an issue here in the Pacific Northwest. And so we'll be, Andrew Dunning will be talking about the geology news today, and then our doctoral student Alyssa Smith will be talking about her work in that part of the country. Andrew, I know it's not a time maybe to talk about all the cool science that's coming out of that, but we do need to know about some of the basics, and I'm looking forward to your presentation on that and other geologic news topics, and then we'll move on to Alyssa's presentation. So I will let you share your screen. Thank you.
All right, let's get started on this month's geology news. It's been a February, not the kind of February I like to talk about, but here we go nonetheless. The news doesn't sleep. I'm going to start with volcanoes because it's been a quiet volcanic month and there's been some cool stuff going on. There are 28 ongoing or new volcanic eruptions all around the world with substantial activity at Karangetang, which is in Indonesia, right down here. There are 2 craters currently erupting, spewing cinders and lava. This is on the same mountain. 2 different vents are open. Looks really cool. And at Semisopochonoi, which is ash plumes into flight lines in the Aleutian Islands out here off of Alaska. And then in Trident volcano, which is in Southwest Alaska, there's been some interesting unrest going on. So Trident is in Southwest Alaska, part of the same caldera system as Katmai, which is a national park as well, and Nova Rupta, which produced the largest volcanic eruption of the 20th century in 1912. The last activity from this volcanic center was in 1953, but the Trident Volcanic Center is composed of 3 dacitic stratovolcano cones. They say 3, but in this Alaska Volcano Observatory photograph, there's very clearly 4 peaks here, but that's neither here nor there. But anyway, back in August, the Volcano Observatory started detecting earthquakes below this area about 20 kilometers deep. So this is very low in the crust. And over the subsequent several days, these earthquakes migrated upwards to the shallow crust, 5 to 6 kilometers deep. And up to now, they've been recording about 10 earthquakes per day below the volcanoes. So magma's moving upward. They're getting something called seismic tremor, which is sort of a seismic rumbling that you can only detect on seismometers that reflects magma moving. Really, not even necessarily magma, just fluids, period. So we know magma has moved into the shallow crust below the volcanic center, but there's no way of knowing if or when an eruption will occur. They keep a close eye on this volcanic center because of its history of large and impactful volcanic eruptions. Now on to earthquakes. The largest event of the last month was a magnitude 7.8 in Turkey. That's this one right here. It was followed a few hours later by a magnitude 7.5. The main shock, the 7.8, occurred at 10 kilometers depth, so quite shallow on the East Anatolian Fault, which is the 2nd largest fault in Turkey. And it's the largest East Anatolian Fault earthquake since 1822. The magnitude 7.5 was a triggered earthquake on a subsidiary related fault system. I'm also going to point out this earthquake here, which happened on Thursday in Tajikistan. This is a 6.8, so an order of magnitude smaller of an earthquake. But remember that, I'll point that out again a little later. There have been a lot of major aftershocks for this 7.8, 7.5 sort of event. there have been a magnitude 6.7, a 6.3, and two 6.0s as of yesterday afternoon. And this map shows only the ones above magnitude 4, but there have been hundreds of aftershocks from these earthquakes, weakening the many, many thousands of already damaged and weakened buildings. The regional geology is fascinating and very complex. The rupture originated right about here on the northernmost leg of the Dead Sea Transform Fault, which forms the plate boundary between the Arabian Plate, which underlies Saudi Arabia, Yemen, Oman, etc., and the African Plate, which is cruising northward, subducting underneath Turkey and Europe. And that's why we have volcanoes here in Greece and in Italy, and also a lot of seismic activity going on. The Arabian Plate and the African Plate are sort of pushing on the Anatolian block and squeezing it out like a watermelon seed between the Eurasian Plate. So this is escaping towards the west. We get the similar tectonic settings in, in the Himalaya, the Tibet, and there's another block there that I can't remember, but colliding plates are basically squeezing crust out. And that's what's going on here in Turkey. So we get the North Anatolian Fault, which runs along the northern edge of Turkey, and the East Anatolian Fault, which cruises through, through the eastern corner. But the main rupture started on the northern end of this Dead Sea Transform Fault and then immediately ruptured east and southwest along the East Anatolian Fault, and ruptured basically from here all the way up to about here where these two arrows are. This is about the same length of fault rupture as the 1906 San Andreas Fault San Francisco earthquake. So that's a good analog. It's actually a perfect analog from the similar tectonic setting. Earthquakes of this size, 7.8, tend to rupture, we plot them as a dot here on the map, but they actually rupture enormous areas. This rupture area, just from the aftershock map, is over 300 kilometers long, 40 kilometers wide, and 20 to 30 kilometers deep. So it's the entire depth of the crust in a three-dimensional sort of zone of squishing and deformation that, it's really difficult to comprehend just how much rock is moving in this area. But a few hours later, as a result of the massive stress changes that occur in the crust from this reorganization of rock and stress, this ruptured about 100 kilometers of the Surgu Fault over here. That runs more or less east-west oriented and connects with the East Anatolian Fault up here. For a understanding of the way earthquakes release energy and how often they occur, there's this fantastic USGS plot. I reference this all the time personally. It's really good visual. So we start to feel earthquakes here about magnitude 3 in most places. And a magnitude 3 earthquake right here is about the same amount of energy as the unfortunate Oklahoma City bombing attack. So that's a truck full of ammonium nitrate. And we get about 130,000 of those a year. It's a pretty common earthquake. We get lots of these all the time in California. We even had one in New York of this size just a day after the Turkey earthquake happened. And then up here in the magnitude 7 area, we get about 15 of those a year. So that's Nisqually 2001. Same amount of energy as one day of a major hurricane. Gets released in about a minute. Up here in the great earthquakes, as they're called, that's your San Andreas Fault rupture. That's your Mount St. Helens eruption amount of energy. That's the Turkey earthquake here with this SAR. So the Mount St. Helens eruption lasted, I believe, 8 to 10 hours. And that same amount of energy was released in about 80 seconds in the Turkey earthquake. So this is equivalent to 295 billion tons of TNT, which is, you can't grasp your head around that. That's just enormous. And most years will get one or two events that size. And then above that, you have your Cascadia subduction zone, your Japan, your Chile. We get one of these every few decades. And this Cascadia subduction zone earthquake, between that and Chile, 1960, the most powerful earthquake ever recorded, the amount of energy released there in a couple of minutes would power the United States for 2,000 years. And this is all stored in elastic strain in the crust. So as tectonic plates are moving and grinding past each other, they are bending at depth and storing energy like a spring does. And eventually that elastic strain, that energy, becomes greater than the frictional strength of the locked fault between the two tectonic blocks. And that's when you get an earthquake. And in the event of this Turkey earthquake, at the epicenter down here, at depth in the crust, several kilometers deep, there was 37 feet of elastic strain that was released in 80 seconds. That we did not get that much slip on the surface, only 5 meters, so only 15 feet of lateral displacement here at the surface along the fault at its greatest, but it's just an incredible amount of energy. There was extreme heavy damage across southern Turkey, as well as in Syria and Lebanon, and it was felt as far away as the Sinai Peninsula in Egypt. There were some felt reports from Cairo, but that's far enough away that they need to be taken with a grain of salt. A seismologist in Japan, I can't remember his name, but they know their stuff, claimed that he thought it was the worst crustal earthquake in the last 100 years in terms of the severity of the shaking and the damage it's occurring. It incurred. There were widespread collapses of high-rise apartments in about a half a dozen major cities along the length of the East Anatolian Fault. There were a number of them that collapsed during the main earthquake, but quite a few of them also collapsed during major aftershocks. The main earthquake was strong enough to weaken a lot of buildings to the point that much less energetic aftershocks just pushed a lot of buildings over the edge. And the most common thing we saw was this kind of pancaking. We don't see this in a lot of earthquakes, but there's certain kinds of concrete post and beam construction, it's called, that just causes tall buildings to pancake. Saw this a lot in Mexico City in 1980 something or other. But over 50,000 people were trapped inside pancaked and collapsed buildings. And as of last night, over 51,000 fatalities were confirmed in Turkey and Syria combined. So that's, that's half the population of Bend. That's just an enormous amount of life lost. And it's just incredible. There were over 167,000 buildings destroyed or damaged beyond repair, and including 80% of all of the buildings in the city of Antakya, which is the ancient city of Antioch. This is the same metropolitan center. 1.5 million people have been made homeless across Turkey and Syria. Buildings like this citadel in Aleppo in Syria that have stood for 2,000 years and survived countless earthquakes of this size were, it takes a lot to damage a 2,000-year-old castle, and walls of this castle have just crumbled. But Turkey has strong modern building seismic codes that have been motivated by the dozens of major earthquakes they have seen over their the times of modern seismology. But particularly in southern Turkey, in the last 20 years or so, they have gone largely or entirely unenforced as a result of, frankly, corruption. It is easier to just pay a fine for not building your building correctly than it is to build it correctly. So ultimately, tens of thousands of the casualties from this earthquake could have been entirely prevented by enforcement of building codes.
And Andrew, it seems appropriate to become momentarily speechless at the magnitude of loss of human life. I do appreciate delving into the science and your thoughtfulness about that. Are there any lessons that we can take for here in the Pacific Northwest from a crustal earthquake of this magnitude?
That's tough to say. I mean, stuff like this is the reason people get into seismology a lot of times, in that, so that 6.8 earthquake I mentioned in Tajikistan happened in one of the most remote areas in the world. It might have been felt by a couple thousand people, but that doesn't matter. That's not a disaster. Disasters happen in populated areas. An earthquake happens in Antarctica, nobody knows about it, nothing happens. A major earthquake happens underneath metropolises of millions of people. And for example, in Japan in 2011, one of the most powerful earthquakes ever, the loss of life was not in collapsed buildings, it was in tsunamis dominantly, which is something you can't really engineer against, but you can engineer against an earthquake like this. And they do that in Japan and in Chile and all over the world, but that was not the case in Turkey. So this was largely a preventable disaster. And it's why it's important for public officials to acknowledge that these things exist and are largely preventable disasters. And that's why it's important to figure out where our seismic sources are, something we're doing every year here in the Northwest, finding new faults, figuring out how often they create large earthquakes, and working to update and enforce our seismic building codes. And that's the main takeaway, that the sobering takeaway we should have from Turkey this month is that this is preventable. We can engineer against it, and listen to seismologists when they say earthquakes will happen here. That's all I have to say about this event, really.
Thank you.
And that's all I have for this month. Just didn't feel right coming up with all the other fun, cool science that has come out of this. Maybe in the future I'll talk about it a little bit, because there's been a lot of very interesting data. These kinds of earthquakes are rare enough that they are integral. When they do happen, we end up learning a lot about the way earthquakes happen and the way they move the ground surface. So every earthquake we get here, anything like this, informs the next generation of building codes. And it's just unfortunate that it has to happen like this sometimes. So that's all for February's geology news. I'll see you next month.
Well, thank you, Andrew. And Carrie, I've been talking a lot. Did you have any other questions, or were there any questions in the chat that you wanted to bring to our attention?
There was one observation of one of the photos that possibly the building that was standing in the upper right image might have been constructed a little bit better than some of the others. And what will be interesting, by the way, thank you, Andrew. That was really good.
Very good.
I think that one of the things that I think will be interesting as follow-up is, from the country standpoint, is what percentages of the buildings that survived were constructed properly. And I think the take home for us, especially living here on the east side of the Cascades, is recognizing that infrastructure that we have, the bridges, the hospitals, the police stations, that the areas that we're going to be needing for emergency services are built to standard so that when that need arises, the east side can become that secure safety hub for the rest of Western Oregon.
Well, thank you all. I think we're ready to move on to our next presenter, and that is doctoral student Alyssa Smith. Alyssa, I should have prepared a biography for you, and I really didn't. So I'm going to kind of leave that to you to tell us a little bit more about yourself. But we're very fortunate to have you, your enthusiasm about the Geological Society and your fascinating research. So I'm just going to hand it to you to do your own introduction, your own biography, and then give your presentation.
Sure. Thank you so much. I'm going to keep it short and sweet because condensing a 45-minute presentation down to a shorter format proved very challenging. So I want to leave as much room for that as possible. So then also, if anyone has questions, I can address those as well. But long story short is I was born in Central Oregon and moved to California in 2001 when I was 11. And I did all my schooling down there. I got my undergraduate from Sacramento State. I did my master's at Northern Arizona University, and then now I'm here at Portland State. Yeah, that's the short of it. If you have any more questions, I've started coming to a lot of the GSOC events. I'm always happy to answer questions. But let me just delve right into my presentation here. And I did do a run through yesterday so I could work out the bugs. Okay, so my topic today is going to be magmatic sources and tectonic implications for Miocene volcanism of the Irtysh quarter of central Anatolia, Turkey. So this was my master's work. I finished my degree a year ago. Actually, a year ago yesterday was the anniversary, or was when I actually did my defense. So kind of funny. But kind of to keep things a little bit more like friendly to people of all different geologic backgrounds, to shorten the title, I'm essentially looking at mantle sources for volcanoes in a certain part of Turkey and what they mean for the tectonic development of the area. So I want to start with a picture here that is looking at the quaternary, much younger Mount Irtysh, which is the stratovolcano in the center here. Let me grab my pointer. So right here, as seen from the eroded remnants of Miocene volcanoes that have been eroded down to just mere hills. So the hills that don't really look that exciting are the stratovolcanoes I'm going to be discussing today. So our story begins in the Eastern Mediterranean region, so specifically in Anatolia. So Anatolia is defined as the portion of modern day Turkey that is within the Asian continent. So this here is a tectonic map that was adapted from the Schleifarth et al. 2017 study. And this shows the location of tectonic plates as well as tectonic blocks that make up the Anatolian crust. So this is then overlain with a geographic map that shows the outline of the country of Turkey. And again, there's a little inset box here if this is a less familiar part of the world. So also included on this map are major fault zones and suture zones and locations of trenches. So I want to call attention to the Cypress trench here, or the Cypress slab, which is going to come back in future slides here. So central Anatolia is not so much a geographic distinction as it is a tectonic distinction. So this is bound between subduction to the west in Western Anatolia over here, so just pure subduction, and then Eastern Anatolia to the east, where it's ongoing continental collision. So at present, and Andrew mentioned this, Central Anatolia is undergoing what's called tectonic escape. So collisional stresses to the east have been manifested along these fault zones here, the Northern Anatolia Fault Zone, as well as the Eastern Anatolia Fault Zone. And this is essentially creating a wedge shape, which is extruding Central Anatolia eastward. And this is just the most recent stage of a very complex tectonic and magmatic history. This interplay of tectonics and magmatism was the focus of the Continental Dynamic Central Anatolian Tectonics, or CDCAT project, which was an international interdisciplinary project funded by the NSF. And what this study sought to understand is the connection between cyclic magmatism and convergence that has gone on since the late Cretaceous, or about the past 100 million years. So the most recent cycle of this in Central Anatolia is thought to have begun with flat slab subduction at about 50 million years. And then this followed with slab rollback, which reignited volcanism after about a 20 million year lull. So if I'm going to be talking about flat slab subduction and slab rollback, I want to start this by explaining kind of some of these ideas. So in typical subduction, we would have two tectonic plates coming together. So here I have oceanic crust in this dark gray and continental crust in this brown here. And then we'd have one plate sink below the other, subduct at some angle. This is important. And then melt could then be generated in the mantle between the two plates. And the mantle in all of my diagrams moving forward is going to be green. So I just want to point that out. Once you generate melt down here in the mantle, that can then pass through the crust and erupt as volcanoes. So this is the situation we have with the Cascades up here in the Pacific Northwest. In the case of flat slab subduction, we'll have those plates moving together, but the plate that's subducted is subducted at a shallow angle, which means effectively you don't have that mantle wedge between the plates. This is simplified, of course. But then over time, what happens is the downgoing plate can begin to roll back. So you'll have an earlier position in the dark gray and then later in the light. You get an influx of hot convecting mantle material in there, and then you can generate the melt needed for volcanism. The way this can manifest at the surface is that you get an area of older volcanism, and with progressive rollback, that volcanism progresses trenchward. So that's important here. I'm going to breeze over this one here, but these are two diagrams to illustrate this model in Central Anatolia. So I've got the cross-sectional view as well as the mapped view here. So I mentioned at about 50 million years, we had a shallowing of the Cyprus slab that's attributed to both collision in the east and also rapid advancement of the Eurasian plate trenchward. So this is thought to have shallowed the slab, which effectively cut off magmatism that had been ongoing before this point. So this lasted for about 20 million years. And then at some point after about 20 MA, it's thought that the slab started to sink, which allowed for an influx of that hot material. And this produced volcanoes in the region. So in Central Anatolia, this created the Central Anatolian Volcanic Province, or CAVP, which is how I'm going to be referring to it going forward. This is an expression that is thought to be the result of slab rollback. So the CAVP, again, Central Anatolian Volcanic Province, is about 250 kilometer long chain of volcanic centers that developed since the late Miocene. This includes about 19 polygenetic centers and many more monogenetic fields. So of the polygenetic centers, Mount Urchis and Mount Hassan are the best preserved. So Mount Urchis is here with this yellow star, and then Mount Hassan is this red star here. So these are the best preserved morphologically and the most studied as a result. So there's a range in lava compositions throughout the CAVP. Recent studies have shown that there's been a general progression of initiation of volcanism from the northeast to the southwest. And this is evidenced by younging volcanism in this direction. So younger volcanism has occurred behind this initiation front. And the most notable for this study is Mount Urchis. So this is nestled in amongst some of the oldest volcanism in the region. So early geochemical studies of this region postulated that this was a result of subduction. This is due to the abundance of calc-alkaline intermediate to silicic lavas with arc-like geochemical signatures. But with more studies into the geology and tectonics of the region, this interpretation has largely fallen out of favor. The way that they have explained the subduction-like geochemical signatures in the CAVP lavas is they've interpreted this as episodes of prior subduction that have altered the mantle underneath rather than active subduction. So this has then led to more in-depth studies of mantle source components for the CAVP lavas. So this is a cross-sectional little cartoon I made to illustrate the different mantle components that have been used to describe the lavas in this area. This is not to scale. First of all, we have a crust that's about 30 to 40 kilometers thick in the area I'm looking at. And this is an amalgamation of accreted Gondwanan terrains. So just from prior episodes of subduction and accretion. Beneath that is the ambient upper mantle. This is this AUM component. And this is thought to be an E-morb or enriched morb-like source. And this is a host to the next component, which is this SMM here, or subduction modified mantle. So this is the shape of these is not necessarily it. This is how I did it to visualize for myself, and I found it effective. But these are bits within this AUM component that have been altered from previous subduction. Beneath this in this image, I have the cypress slab here. So that's that subducted plate. And this little target bullseye here shows the slab is coming out towards you. So just for getting yourselves oriented. Below the cypress slab is what's called the IPC, or an intraplate component. This is a deeper oib-like, and I have in quotation marks here, astenospheric component that may have been incorporated by flowing around the slab as it rolled back. So most CAVP lavas could be explained with this AUM and SMM alone, but there were some recent studies that found that a third more OIB-like component was required to explain the chemistry. And the Read It All investigation quantified this IPC as about 10% contribution to some of the younger lavas, so far subordinate to that AUM and SMM contributions. And one thing I want to highlight here is if some of these terms like EMORB and OIB are unfamiliar terms, the important takeaway here is that they're different mantle components that require different tectonic environments to get them incorporated into lavas. So that brings me to my study area, which is the Urchis corridor. This is a recently penned name for a collection of 7 stratovolcanoes. They're highlighted here in the red in the CAVP. So these are along a pull-apart basin surrounding the younger Mount Urchis volcano. Recent argon dates for the Urchis corridor place these at about 12 to 3 million years old, and they're at the northeasternmost extent of the CAVP, representing the oldest volcanoes in this region. Previous CAVP geochemical studies have predominantly been conducted on Pliocene to Quaternary aged volcanic centers, such as Mount Urchis and Mount Hassan, and some of the various monogenetic centers in this area, with little focus on these early eruptions that may have accompanied slab rollback. So what I'm going to be doing then is giving a brief overview of their chemical affinities, and then use those to discuss potential mantle sources that could have produced these lavas. From there, I'm going to compare them to other CAVP centers and discuss that in context with the slab rollback model. So the hypothesis is that if a deeper intraplate-like mantle component contributed to the younger CAVP lavas, but was not incorporated into early CAVP lavas, this then may reflect the progression of slab rollback in central Anatolia. So my goal with the next few slides is to hit the high points with the chemistry. So I'm leaving out a lot, but I kept the really important parts. And then I do have some slides at the end if there are questions into some of the nittier grittier chemistry. I'd be remiss if I didn't start with what's called a total alkali versus silica diagram. This is after Labas et al. So I included the Urchus corridor lavas here, as well as a compilation of other CAVP basalts, which are the gray X's. So this is a very general classification for volcanic rocks, just based on their chemical composition. All in all, the Urchus corridor lavas range in silica from about 50 to 70 weight percent silica, with the majority of the samples greater than 52 weight percent. So samples, lavas with silica content greater than 52 weight percent, I'm referring to as evolved, which just means higher silica content than basalts. So basaltic andesite through dacite in this. So I'm going to further subdivide the evolved lavas into group 1 and group 2, which is why we've got two different sets of symbols here, which I'm going to discuss shortly. This symbology is going to be consistent throughout though. So basalts are going to be the blue diamonds, basaltic andesites, the green squares, andesites, orange triangles, and dacites, red circles. So I will have a key on most slides. If for some reason I keep them on there for myself too. So these are rare earth element diagrams for the Urchus corridor lavas. These are normalized to chondrite. I could go on for hours about these, but I won't. I'm going to keep it very simple here. So I have a diagram that just includes the basalts and then the two different evolved groups. I kept the basalts on here just for easier reference. What we see here very generally is that Urchus corridor lavas tend to be enriched in light rare earth elements. So left side of this chart with respect to the heavier, which is on the, or I said wrong. So light is left and heavy is right. So there's no really significant anomalies. You see a small one in cerium, but that's a really squirrely element to analyze. So I wasn't too concerned. Generally, there's a big range in rare earth behavior in the evolved lavas, and the basalts tend to be a little bit more tightly clustered. What's really important to see here is that the basalts overall have a less steep rare earth element pattern. If we look at one way we could look is that overall lanthanum ytterbium ratios tend to be a lot more consistent versus the evolved lavas, that there's a much wider range. So looking at the whole slope. But even so, they have a pretty similar dysprosium ytterbium values, which is just looking middle to heavy. So this leads to crossing rare earth element patterns. You can see lower basalts to end up in a more higher range in these. This is very important when discussing sources. Because if you're looking to see if basalts represent the parental melts for those more evolved lavas, it is very difficult to explain it with simple models if they have crossing rare earth element patterns. So this is a big suggestion that these basalts in this area actually have significantly different origins as compared to those more evolved lavas. I did a number of isotopic analyses for this. I'm showing the epsilon hafnium here. So that's just, that's a way to represent hafnium isotopes. So I have the Urchus corridor lavas as well as all of the other areas that have hafnium data in the CAVP, and you can see there's not very much. We use what we've got. So there's a range in the evolved lavas here from about 2.6 up to 10.1. The basalts tend to be intermediate to the evolved lavas here, ranging from about positive 5.6 to 7.7. And looking at the epsilon hafnium versus silica, you're starting to see what I've been foreshadowing with these two groups of evolved lavas, which is what I'm going to discuss next. So I previously suggested that the basalts don't look like they represent the parental melt for the evolved lavas. The strongest line of evidence is those crossing rare earth element behavior. And then some important isotopic differences, which I'm going to be going into further in the next few slides. But essentially, you cannot derive higher isotopic concentrations or higher isotopic signatures in the group 1 lavas from the composition of the basalts. So you can explain this via crystal fractionation or assimilation from a single source. And for this reason, I'm going to discuss the evolved lavas and the basalts separately. So the evolved lavas look very similar at the surface, similar mineralogy between samples of the same silica range, and broadly similar in major and trace element behavior. But the biggest difference and the most compelling is in the isotopic composition. So we begin to see discrete groupings in these evolved lavas. We've got a subset of evolved lavas with relatively invariant epsilon hafnium values, a median value of about 8. And then another subset which extend to lower epsilon hafnium values. So I designated this group with the relatively invariant epsilon hafnium values as group 1. So this is this uppermost gold group here. And then those with the variable epsilon hafnium, these lower circled groups here, as group 2. So crystallizing minerals cannot differentiate between different isotopes of the same element. So what this means is that lavas that form from a single source should have uniform isotopic compositions. So lavas with variable isotopic concentrations have to require an additional input to change those concentrations. So I'm going to call attention now to the other things that I have on this graph, which are the Kula basalts, which are from Western Anatolia, the Hassan monogenetic cluster basalts. Both of these are, so the Hassan monogenetic cluster is to the southwest in the CAVP, a younger center. Both of these groups are said to be primary mantle melts. So given that the epsilon hafnium values of the group 1 lavas are similar to the majority of the included basalts, these lavas may have evolved in a relatively quote unquote closed type system where crustal contamination was negligible. So this is supported by major and most trace element behavior. Took those slides out for a time, but I do have them at the end if there are questions. And then group 2 has variable epsilon hafnium. So I'm calling attention down here to these gray squares, which are Cappadocian ignimbrites. So these are rhyolitic, highly evolved melts that are interpretive to assimilated up to 80% crustal material as they differentiated, and these are crucial. So what we see is that these G2 lavas have the generally lower epsilon hafnium concentration that start to approach those Cappadocian ignimbrites. And this suggests that these lavas evolved in a more open type system where they assimilated some amount of crust. So going to the basalts then, if we say they don't represent the parents of these evolved parental material, then we can go and compare them instead to other CAVP basalts. So what I chose to do here is so first of all, looking at Mount Urchis, this yellow star, which is a difference in time, but in the same area, as well as basalts of the Hassan monogenetic cluster down here, which are both a spatial contrast and temporal contrast. So I'm just touching upon some isotopic dissimilarities here. I didn't have a separate slide for this, but this is 207, 204 lead versus 206, 204 lead here, just to highlight the dissimilarity of the Urchis quarter basalts to the Hassan monogenetic cluster and the Kula basalts. So that's, again, there's not a lot of isotopic data in this area, but we use what we have. So this is a diagram I didn't include for the other lava types, but this is a mantle normalized incompatible trace element diagram. Say that 3 times fast. Looking at the Urchis quarter basalts as compared to those from Mount Urchis, which are the brown symbols, and the Hassan monogenetic cluster, which I used a range in the values in the gray here. So despite differences in isotopic composition, incompatible trace element behavior is pretty similar. But the variability in some of the most incompatible elements on the left side here is pretty apparent, as well as some important things like discrepancies in niobium tantalum slopes. I could go into that more, but what this highlights is that minor variations in these elements between lava suites may be significant, or the devil's in the details. So I'm going to use one paired ratio of elements to kind of highlight these differences. So this is thorium ytterbium versus niobium ytterbium diagram. What I want to call attention to is that we have an array here that represents all morbs and oibs globally, as well as the AUM component that we cited as being a potential source, an SMM component, again, another source, as well as the Kula basalts, which are that proxy for the IPC component. What we see here, first off, is that more depleted sources will have low thorium ytterbium, niobium ytterbium. More enriched will have higher thorium ytterbium, niobium ytterbium. So if we just have elevated thorium ytterbium without an increase in niobium ytterbium, that could be a sign of subduction enrichment. What we see here is that the Urchus corridor basalts have no lower niobium ytterbium values compared to the majority of other CAVP lavas, and they're towards the more depleted end, more towards this AUM component. So thorium ytterbium and niobium ytterbium systematically increase from like Mount Urchus samples into the Hassan monogenetic clusters. And so also this thorium ytterbium, this variable values in the basalt probably reflect that variable subduction enrichment, but altogether more towards this AUM component than any other CAVP lava. And also, I want to highlight the absolute dissimilarity to that IPC component that's been called on for other areas. So what I found is that the Urchus corridor basalts generally reflect that melting of that AUM component, and that's the contrast to the variable contributions of all three components in the Mount Urchus and the Hassan monogenetic cluster basalts. So that incorporation of that IPC component is therefore not required to explain the chemistry of the Urchus corridor basalts. And heading to wrap this up, but trying to take it back, the evolved nature of the G1 lavas, as we discussed that it could be from differentiation without crustal contamination, there's an idea there that those still may retain some of their signatures of their mantle sources. So if we just look at the group one, those filled in symbols here on that same diagram I just looked at, these are much more in line with this SMM component, still a little lower thorium ytterbium. This shows that there probably was a greater incorporation of that SMM component in the parental melts of these. Discrepancies in these values, I'm really glossing over a huge part of my thesis here. Discrepancies in these elements could potentially be from fractionation of trace minerals, because major minerals such as plagioclase, pyroxenes, hornblends would not be able to appreciably shift these elemental concentrations. So any discrepancies in here are potentially the result of trace mineral fractionation. Just bringing that all back to show everything visually. I established that those basalts are most likely a result of just this AUM component, whereas the group 1 lavas have both the AUM and SMM contribution, and then the group 2 lavas, these two plus probably some crust in here as well. And the big interpretation from this is that for younger lavas in this area, the recent studies have called upon a deeper seated oib-like component to explain their chemistry. Under the slab rollback model, involvement of that deeper astenospheric component in melt generation could potentially reflect upwelling of deeper mantle material to fill in behind the cypress slab during rollback. So the absence then of that oib-like IPC component in the Miocene to Pliocene aged Urchus corridor basalts, then incorporated into the later Quaternary volcanoes, could then reflect that progression of slab rollback. So with that, just to kind of summarize everything, This study aimed to characterize these lavas from these little studied Miocene age volcanoes of the Urchus corridor to discuss these in context of slab rollback. And what I found is that the basalts in this area don't represent the parental melts of the evolved lavas. And this is due to differences in trace elements like crossing rare earth element patterns and isotopic differences. So the group 1 lavas likely reflect crystal fractionation with negligible crustal contamination, whereas the group 2 lavas more likely reflect evolution with some crustal contamination. Those Urchus quarter basalts look to be sourced predominantly from the ambient upper mantle component, and the lack of that deeper seated component in the Urchus quarter basalts that is seen then in younger basalts in other areas of the CAVP then may reflect the progression of slab rollback in this area. And with that, thank you so much for listening. If anybody has any questions, I would absolutely love to answer those.
This is from Paul, and he says, what causes flat slab subduction as opposed to subduction at a steeper angle?
This is a wonderful question and a very important one. So I want to bring it in here. So one of the most important things for flat slab subduction is convergence rates. So what's the thought in this area is that if you have the plates coming together very quickly, I don't know the physics behind it, but I know that what happens is if those convergence rates are really fast, a lot of the times that's just when you get the flatter slab there. So it could be a reflection of that. Sometimes it can be a reflection of density. If you have like a really young oceanic crust that isn't quite as dense, I know that those ones can come in at a more shallow angle, whereas the denser plates, the older crust is more easily subducted and just goes down a lot smoother. Densification is actually one of the reasons that you can get slab rollback. So if you have a plate that isn't dense enough at one point, it can eventually lose enough volatiles and water and be densified and start to actually roll back. So densifying is actually a word, surprisingly. Not making that up, but yeah, there's a few different things that can cause it. But yeah, the fast convergence rate is thought to be the main driver here for this area.
And that's controlled by seafloor spreading. When seafloor spreading is more rapid, then it's going to shove in, faster.
There's not seafloor spreading in this area. This is all convergence. So this is Africa moving towards, and I do not believe there's any spreading involved in this area.
Okay, so John had a question. Is it possible to compare the volcanic formation in Turkey to similar volcanics in the Portland area? It seems that both areas have a combination of stratovolcanoes as well as monogenetic volcanoes like the boring volcanics, which actually that leads into, I was just surprised at the youthful nature of these volcanics that you're looking at, and that comes back to our Portland areas. So thoughts?
So actually, I am the right person to speak on this, but not for the reason that would come across in this talk. My doctoral research is in the Cascade Range. So I am looking in this area moving forward. And actually a lot of what we have in this area, so the volcanoes that I looked at in Turkey are significantly older than the high Cascades, more akin to the middle of the Western Cascades. What's happening here is mostly just pure subduction in the Pacific Northwest. But the flat slab subduction is potentially something that's been used to describe volcanism more in the Southwest of the United States. So this is something they've looked into to describe things like the Colorado Plateau and some of the volcanism in that area.
So like the Flagstaff area?
Yeah, and that's where I did my master's. So yeah, that's a complex area.
Yeah, having worked there and worked with the mineral materials, the cinder cones, and it was always a surprise coming up through those limestones and sandstones. It's like, holy cow, how did you get here?
The
What's going
scoria
on?
cones out there are a different breed. And that's one thing I hope in one day in the future, I can start to look at those as well, because they're fascinating and there's not enough research done out there.
So we're right at our hour. So thank you everyone for coming, and Alyssa and Andrew for their wonderful presentations. We always keep the room open for another half hour so that once the recording is off and you're not intimidated by asking a question when you're being recorded, you can stay and chat. And again, Alyssa and Andrew, if you want to stay and answer any further questions or contribute to any more of the discussion, please do. Again, thank you both for today and for everyone else for coming. And I hope everyone has a nice and wonderful and warm rest of their day. Thank you.